All right, so welcome back. So here is the here is the Alpha Suite. We can see all these quite a few different projects that have already been solved. So if you look at the notes here, we got 0 degrees, -6, -4, 2 degrees, -2 degrees, 4. So yep, we go all the way up. I think so. Here's 14. And this is 16, but I don't think I actually put that in yet. Anyway, so yeah, again, I went through so I loaded up I imported the base geometry and then did the rotation each time, made the enclosure. You have to rotate before you make the enclosure. Boolean, meshed it. You actually see in these notes, sometimes I write other little notes I did. I noticed that as with some different rotation angles, you had to use different meshes. Sometimes it would fail. So again, just like increase the quality of the mesh, so make it fine. A few of them I had to do, set it to tetrahedron, especially towards the end at like 12 degrees, and you'll see that later. But yeah, and then just go through and solve it. Took about 7 minutes each, so took quite a while to get one, but the results are worth it. Oh, also over here at the 10 degree test, I copied over the geometry into another test and ran the 4 equation model, the SST model, just to compare results with the 1 equation model. So and notice that they're actually pretty similar. Actually, I have them here. So for the SST, showing like a lift of 191, and then for the 1 equation 183. So drag and lift, pretty close. That's within 10%. Yeah, within 10%. So I mean that's actually pretty significant off, but it's not terrible. It's in the ballpark. So going back here. Also, I think I misspoke earlier. The XYZ forces are representative of lift, drag, because the way that the Cartesian coordinates are set up, it's set up along the free stream. So Y will always be lift and X will be drag. So I misspoke earlier. We don't have to use the direction cosines to actually get the lift, which will make our analysis easier. So before we examine all of these and save you the trouble, I already took a picture of all of them. I'll bring up the results for the SST one, so we just kind of look around what it looks like. It looks pretty cool. So this is at 10 degrees angle of attack again, and it is the SST 4 equation model. So let's hit the Z. So you can see the 10 degrees angle right there. So let's get streamlines. No, that looks bad. Let's get the leading edge velocity first. So you can see it hasn't really changed too much from that angle. You can definitely see the vectors start to come off the nose as it's just getting displaced, basically. We got our fast velocity. So that's right over here. That's a cool one. So you can see right at the top, the velocity is really fast as it gets in that low pressure area. And I think my favorite one, pretty cool picture of the wing vortices from the back here. If we pan over, really nice in the wake there. Really nice on each side. You get these nice vortex. So that looks pretty awesome. And then also the rotate pressure contours, you can see clearly. Anyway, just wanted to show you that before we look into the other studies. So save you the trouble of opening up each solution and getting all the forces. I already did all that, so it takes a while. You have to open up each solution and then do the print the forces so you can see. So for each angle of attack, I had a nice picture at the isometric view, and then took the lift and drag forces. So you can see, and keep in mind the scale here. So as we go to 4 degrees, pressure is definitely dropping lift goes up, drag goes down. So the colors aren't exactly on the same scale. -2, lift goes up again, drag continues to drop. You can also see the stagnation points kind of shift downwards as we increase. And then 14 to 0 degrees, 14 pounds of lift. And now when we start getting into 2 degrees, you really start to see the pressure drop as it goes over the leading edge and goes over the wing. You can see the lift's increasing. Velocity's going even faster there. Keep on going. I noticed in 12 degrees the mesh looks pretty bad. Yeah, I noticed I didn't want to rerun the calculation, but I mean the values aren't actually that bad. It goes from 41 pounds to 42 pounds back to 40 pounds at 14 degrees. So in 14 degrees, so you can see here it looked bad. I actually used the tetrahedron model on 12 degrees. But I think I forgot to change the mesh resolution from medium to fine, which I did do in the 14 degrees. So you can see the mesh actually looks good here, even though I used the tetrahedrons. But that one looks pretty bad. I didn't really want to redo it. We have a lot of data, and it's not actually that bad. It's follows a trend, so that's good. In the 14, you really see that adverse pressure gradient and flow separation. If we were to rotate it around, you can see some it's a little red on the tip, on the trailing edge. So there's some nice flow visualization and all those forces. So let's bring this to get the drag pole. We're gonna have to bring it over into MATLAB. So let's do that. Bring up the command menu and just copy in all these force vectors. Get a nice. Oh, here we go. Force is equal to, and then we'll just go down the line, copy in all these Cartesian, or actually, sorry, resolved lift and drag forces, and that other random force, side force for each angle. And we'll see what we get from all of this in MATLAB. You can see there at 6 degrees it's getting like about a 2G, 6 degrees angle of attack at 2Gs on the aircraft, which weighs about 15 pounds. And there's all of them. So there's force. Let's just copy that in, see what it does. Alright, so now we got some force matrix. Let's turn it into lift here. So let's get lift is equal to force column 2, and then I'm going to rotate on side. Drag is equal to force. And these are all in English units. So to get the coefficients now, we're going to need the density. So rho is equal to 0.002376, and we also need the planetform area is equal to 8 feet squared. Velocity, we used 59 feet. V is equal to 59 feet per second. And then so we can do Q is equal to 0.5 times rho times V squared. And now to get CL is equal to lift divided by Q divided by S. CD is equal to drag and negative drag because it's negative in the matrix. And there you go. So now we can plot these. Let's just do CL and versus CD versus CL. Make it black holes. And there you go. There's a drag polar. It actually doesn't look that bad either. So here's CL along the x-axis, CD along the y-axis. So like parasitic or minimum drag coefficient around 0.08, which occurs at 0.6 CL. You can see as we get up to the higher CLs, the drag starts increasing rapidly at stall. Yeah, kind of what you expect. Maybe even better. Here, let's make a alpha sweep. So alpha, we got -6, -4, -2, 0, 2, 4, 6, 8, 10, 12, 14. That's in degrees. Let's plot alpha and x versus lift or CL. Check that. And there's, yeah, there you go. There's a lift lift curve that looks pretty dang close. So again, we didn't actually get down to the zero lift portion, and probably be at -8 or maybe -10 even, which is kind of crazy with such a cambered wing. It's ridiculous. But yeah, you can see that tops off at about 1.2 or 1.3-ish CL, 1.28 there at 12 degrees, and there's a little drop off for the stall. Classic lift curve right there. Again, you can see that camber there. So yeah, and then you can really just play around and get a bunch of stuff. So I actually already messed around here, so I'll just kind of run what I already done so you can see some of the things I looked at. All very useful things for capstone, but nothing as valuable as that CD or the drag polar, which you can use to get all your power required, all the stuff you learn in performance, so you can get some nice data for your PDRs in the fall, and then update it and as you go on with your new design. So here's a drag polar. This is actually superimposed with the drag polar that we calculated using I believe parasitic area method. That's the red, versus here's the drag polar we got from CFD with a little curve fit, which ignores the stall region, although not the negative stall region, or negative where it's not linear anymore. Here's a nice, this is what I use to get the K value. Here's a lift curve versus a 2 pi inverse radians. Yeah. Lift to drag ratio, so peak lift to drag happens around 8 degrees angle of attack. Lift to 1/2 over D, so if you want to maximize range, you know, you're going to want to optimize. Oh no, that's for that's for maximizing range for a prop airplane. You're going to use this ratio. You want to maximize. You want to get this as close to maybe your 0 degrees, where you're going to have less drag as possible. So we don't really have the best design here. We're going to have to be all the way at 8 degrees. I made another figure here, kind of difficult to make actually, but it's graphing to get level flight, assuming 16 pounds, what alpha you're going to need to be at various velocities. So you can see like at 30 knots here, you're going to need to be at 2 degrees angle of attack, and you can quickly see as you slow down, angle of attack goes up really rapidly, so you can actually get a kind of a general stall speed. So probably I'd say around 23, 22 knots or so, because if you slow down past that, you're going to rapidly increase the amount of angle of attack. And it's all the drag. This is where you're going to start. This is where flow separation is occurring around here. So this is your stall region. So again, so now we got a stall speed, all that stuff, and then maybe down the road we'll eventually be able to do some CFD where you can change the control surfaces and find, you know, what elevator deflection you need Anyway, tons of cool stuff. You can all of it. A lot of this should be familiar. This will come in your stability control, but all these graphs, they should be pretty familiar to any aero major and pretty helpful for your PDR. So thank you for watching. You can mess around with all this stuff, explore it however you want, but hopefully this helps you kind of see the big picture of how you can actually use CFD starting next semester. Thank you.